right there on top of the moon. We could sit and do nothing. I wish we were bold to just fly away. I don't wanna care. Just be here and I'm good alone. I'll be okay, miss you like an old friend. Too scared now, thinking I should call up. I'm not. There's not much to do when all
Hello, good day. Today we are going to discuss these exact differential equations. And before proceeding to our topic, don't forget to subscribe to my YouTube channel. Okay, so we have these exact differential equations, and we need to consider this standard form of solving an exact differential equation in which we have this m as a function of your x or y variable, dx plus your n as a function also of your x or y variable, dy is equal now to 0. Okay, this is our standard form of a certain differential equation, or you may opt to use this form m dx plus n dy is equal now to 0. So it's either of these two, you may have to use this one or this second equation, but for me, I hope to use this one, since this m will be a function also of your x or y, also your n is a function also of your x or y variables. So I am comfortable of using this m dx plus n dy is equal to 0. Okay, so what is the first step in determining if the said differential equation is an exact? So number one is you need to check the partial derivative of your m with respect now to y is equal to the partial derivative of your n with respect now to x. Okay, so this partial derivative of m with respect to y indicates that your y is a variable, and your y is not a constant. Okay, and in this partial derivative of your n with respect to x, this x is your variable, not a constant. Okay, so try to remember that one, because we will be using that one in our calculation. Okay, so if this would be the case, you will proceed now to the second step. So what is this second step? So we have these solutions. Okay, so what are the solutions, if ever that we comply this criterion of step number one? So we have this 2.1, which we call now the direct solution. Okay, so what is the form of this direct solution? So you have to remember this form, integral of m dx plus the integral of your this quantity, so we will just enclose this one in a bracket. We have here n minus partial derivative with respect to your y of this integral of m dx. Okay, m dx. Okay, and then close bracket, and this is dy is equal now to a constant c. Okay, so try to remember this format if we are considering a direct solution, but you can also consider this indirect solution. Okay, so we have now this indirect solution. So actually we have two, we have two here. Number one is you may consider this integral of m dx plus your function of your y variable is equal now to a constant, or you may opt to use also this integral of n, okay, dy plus a function of your x, okay, equal now to a constant. So these are just the different solutions. If you are going to consider a direct solution, so you have to use this standard form, but if you are going to consider this indirect solution, so you may opt to use this one, or you have to use also this another form, okay. So to better understand the application of this exact differential equations having this form, mdx plus mdy equal to 0, and to determine the exactness of this differential equation, you have to conduct this step number 1 and this step number 2. Okay, so we will proceed now to a simple sample problem. Okay, so find the solution of the differential equation given this 2xy minus 3x squared quantity dx plus quantity x squared plus 2y dy is equal now to 0. Okay, since we already discussed the variable separable, the homogeneous equation, and this exact differential equation is our third topic, so you may ask, why is it that we need to consider this given differential equation that we are going to use only this exact differential equation? So I will just give you a preview of why is it that we need to solve this one using this exact differential equation. Because first, if we consider if this given differential equation is solvable using the variable separable, so we try to check if we are going to use this variable separable. Okay, variable separable, check. Okay, because there may be some problems in the future that you're going to find the solution of the differential equation without indicating what method you are going to use. It could be variable separable, that could be homogeneous, or this exact differential equation, and among others like the non-exact. Okay, so just in case that we are going to find the solution of this differential equation without stating what method we are going to use, so first you have to check for the variable separable, okay, if this can be solved. So the form of our variable separable is dy over dx is equal now to the function of your x and y variable, which is equal now to the j as a function of x times p as a function of y. Okay, so from this given, so we need to have this dy over dx, so probably we will multiply this one with 1 over dx. Okay, so multiplying directly with 1 over dx, so this one will be removed, so only remain is this 2xy, so we have now this 2xy minus 3x squared, and this is dx, okay, plus this quantity x squared plus 2y, and then this is dy is equal now to 0, and then we need to multiply this one with 1 over dx so that we can have this form of dy over dx. Okay, so we have this 2xy minus 3x squared quantity. Okay, and then after that one is we have here plus, so this could be dy over dx already, so this is x squared plus 2y, and then this is dy over dx is equal to 0. Okay, so we need to transpose this one to the other side. Okay, so this would be dy over dx is equal now to, this is negative, no? So we have now this fraction, no? This is negative of your 2xy minus 3x squared quantity, and this is in our denominator, no? So we have this x squared plus 2y. Okay, so can we use this form with regards to this form here? So we try, we just try if this will comply with this standard form. Okay, dy over dx is equal now to, so we will have this negative, no? So the common variable here is your x, no? Okay, so we extract the x, and then we have now this negative x times this 2y minus 3x. Okay, and then the other one is x squared, no, plus 2y, x squared plus 2y. Okay, so do you think this will comply, no? This will comply with the form, no? dy over dx equals to j as a function of your x times b as a function of your y, because this one, no, if this is our x times this quantity here, which is also having this variable x and y, also the denominator is having this variable x and y also this, so therefore we can say that this one did not comply, with this form of dy over dx equal now to j as a function of x times b as a function of y. So therefore, hence, okay, hence the given, you can say that the given equation cannot be solved, cannot be solved by variable separable. Okay, variable separable. Okay, so that is one checking, that this one cannot be solved, by the variable separable, and second is try to check for the homogeneous, homogeneous. Okay, is this one can be solved by using homogeneous equation? So we will check, so from the given, the degree here is, okay, from here the degree here is from this one, we'll just have to put it here. So we have here 2xy minus 3x squared, and then this is dx plus your, we have here x squared plus 2y, and then this is dy, okay, equal now to 0. The degree here is 2, okay, and this one also is 2. Okay, how about this second term here? The degree here is 2 again, but here the degree is only 1. Okay, so we can say that this is not homogeneous. Okay, because in order for this one to be solved, using homogeneous equation, so they have, each term must have the same degree. So we have here, this term here is only first degree, so that is why this will not comply for homogeneous equation. So we cannot solve this one using homogeneous equation. Okay, so this time we will check, if this given differential equation can be solved, no, by using these exact differential equations. Okay, so proceeding, so we try to check, no, try to check if we can solve, no, using the exact. Okay, so according to the steps, no, using this exact differential equation, you need to determine if this one is complied, no, partial derivative of m with respect to y is equal now to the partial derivative of n with respect now to x. Okay, that is the first step, no, for checking if this can be solved by exact differential equation. Okay, where our m here is just equal now to 2xy minus 3x squared, no, this one, and our n is just equal now to x squared plus your 2y. Okay, so this time we try to check, no, the partial derivative, no, of m with respect now to y. Take note with respect to y, so y is our variable. So from here, this is variable y, so its partial derivative is just equal now to 2x, and this one, meaning there's no presence of your y, meaning this is a constant, no, this 3 and this x is a constant, no, so this is just equal now to minus 0. Okay, so since this is considered, no, as this term is considered as a constant, so probably this is equal now to 2x. So how about our partial derivative of n with respect now to x? So in this case, take note x, no, as our variable. So for n, this is our variable x, so this is 2x. Okay, since this exponent is 2 minus 1, so this just simply equal now to 1. So 2x minus plus, so there's no presence of the variable x, no, so we consider this one as constant, so the partial derivative of a constant is just simply equal to 0, so we can say that this is equal also to 2x. So hence we can say that our partial derivative of m with respect to y is equal now to the partial derivative of n with respect now to x, and we can say that it is an exact, no, exact differential equation. Okay, so we can solve this one using the exact differential equation. So our solution for this is, this time we are going to use, no, this direct solution. Okay, we're going to use this direct solution. Okay, so its form is this integral of m dx, okay, plus the integral of this quantity here inside the bracket, this is n, minus we have here the partial derivative, no, with respect now to your y of your integral of your m dx. Okay, and this is bracket and this is dy is equal now to a constant c. Okay, so first we need to consider, no, considering first this, considering this integral of m dx. Okay, so after this one we will proceed now to the second term, so we just go first with this integral of m dx. So substituting, so integral of m dx is equal now to the integral of your m, which is quantity 2xy minus 3x squared. Okay, and this is dx. Okay, so after that one we are going to distribute, no, this integral and dx in each term. So we have here integral of your 2xy and this is dx. Okay, and then minus this integral of 3x squared, and we have now this dx. Okay, so we can say that this is just equal also to integral of dx is equal now to, so dx, no, so our variable here is the x. Okay, so we extract the 2 and y. Okay, so we have here 2y integral of x, and this is dx, and then minus, we have here, we extract the 3 now outside the integral, so this is x squared dx. Okay, so solving this one, so we have here 2y, and then we have here, this is by property, no, if we assign, no, try to remember this property, no, integral of u du is just equal now to u to the n, excuse me, this is u to the n, no. So if you have now this integral of u to the n du, okay, so this is equal now to u to the n plus 1, okay, over n plus 1 plus your constant c. Okay, so you have to remember this one. So in this case, our u is x, no, and our du is dx. So our exponent here is just simply 1. So we have here u to the n plus 1. So we can say that this is, since our exponent is 1 plus 1, so this is x squared, okay, over n plus 1 over 2 plus your c, yeah, plus your constant, where in this case we will assign our constant as c1. Okay, minus 3 times, no, times this quantity. So again, no, our n is 2, our u is x, so using this one, okay, so we have here x, then 2 plus 1, so this is 3, and this is 3 plus a constant, where we will assign our constant here as c2. Okay, so do not be confused, no, because if we are going to use this one, if you will assign now your u is equal now to x, no, so therefore your derivative of u is just the derivative of your dx, no. So from here, do not be confused, no. So our x is our u, and then dx is du. So using this form, so you can actually, no, use this n plus 1. So that is why for this one, this is 1 plus 1, this is 2 over n plus 1, which is 2. And in this case, our n is 2. So 2 plus 1 is 3. So x to the 3, and then over n plus 1. So that is why this is 3. Okay, so do not be confused with this one. Okay, you have just to assign your u equals now to this to this x, and your derivative of your u therefore is also the derivative of your x. Okay, so we are done with this integral of m dx, no, and then simplifying, no, we will distribute this 2y in each term, so we can say that this is 2 will be cancelled out, no, so this is x squared. Okay, this is x squared y, no, x squared y plus your this one, okay, 2 c1 times your y. Okay, and this is quantity, and this is minus, so we remain, no, this minus here, we only distribute, no, the 3, the number 3 in each term, so this is minus this quantity here, so cancelled out, so this is x cubed, and this is 3 times plus c2, so this is plus 3 c2. Okay, so simplifying, no, this is just equal now to x squared y plus 2 C1 times Y minus this. No, we distribute the negative or the minus sign, so minus this x cube, okay, then minus this 3C2, okay. So after this one, we are done with the integral of mdx, no. So this time we will proceed, no, to this term here, the integral of this quantity n minus partial derivative of this integral of mdx with respect now to y, and then afterwards we can solve, no, the solution of this given differential equation. Okay, so proceeding here. Okay, so considering, okay, considering this integral, no, the second term here, integral of your quantity n minus this partial derivative now with respect to y of your integral of m dx, okay, bracket dy, okay. So we need to, actually this integral of m dx, no, we already have here, so we can still use this one, no. Okay, so proceeding with this is just equal now to the integral, okay, of your n minus this partial derivative with respect now to y of your integral of m dx, okay, dy is just equal now to this integral of your n, no. We have our n, which is this one, okay. This is m dx plus n dy, so this is our n, no. So we will substitute the n, which is x squared plus 2y, okay. So we may write here, okay, quantity, okay, x squared plus this is 2y, okay, and then we have here minus, no, minus this partial derivative, no, with respect now to y of your quantity. So I think we have solved this mdx, no, integral of mdx, no. We have solved this integral of mdx, no. So I think we need to have this value, no, for integral of mdx, and we'll just enclose this one with the parenthesis, no, of close, open and close parenthesis, okay. This is integral of mdx, okay. So here, this is our integral of mdx, no, okay. But take note that this is just for the first term here, no. But now we are considering the second term. So still, by solving this integral of mdx, we can still use, not this one, okay. Okay, but your constant here will be a different constant because we already have this c1 and c2 here, no, for this term, okay. So for this term here, no, which is our second term here, for this one, integral of mdx, this is a different constant, no. So we can no longer use the c1 and c2. So therefore, we can say that still we have now this integral of mdx equal now to this one, okay. But we will just replace, no, this c1 and c2 with another constant of c3 and c4, okay. Okay, so if we are going to replace this with c3 and c4, so probably we will have now this one here, no, okay. So our c1 here is just equivalent to c3, and our c2 is just equivalent to C4. So actually we can use this one, no, here. Okay, so this is x squared y, okay, x squared y plus 2 c1. So our c1 will be replaced with another constant, no, plus 2, this would be c3, okay, times y, okay, minus x3, okay, this is minus x cubed, and this is minus 3, and this c2 will be replaced now with c4, okay, and then this is the integral of mdx, no, and this is here bracket, bracket, and this is dy, okay, and this is equal now to, okay, so here integral of, this is bracket, no, so we have this quantity x squared plus this 2y, okay, then minus, so from here you have to take, no, the partial derivative with respect to y, meaning your y is your variable, and any other terms there except y are all constants, okay, so partial derivative with respect to y, taking, no, meaning this y is your variable, so from the first term, okay, we distribute this one, no, partial derivative with respect to y of this x squared y, so we can say that this is just simply, so we have here, no, we remain here the minus sign here, so we only distribute this partial derivative with respect to y, so x squared y, so its partial derivative with respect to y is just simply equal now to x squared, no, since our variable is our y. For the second term, so plus 2c3y, so this is also plus 2c3, okay, and then this one is partial derivative with respect to y, this is a constant, no, a partial derivative of a constant is just 0, and also this 3c4, so this is 0, okay, and this is close parenthesis and bracket, and this is dy, okay, so this is just simply also equal now to this quantity x squared plus 2y, and then minus this x squared, no, plus 2c3, and this is bracket dy, okay, so after that one we are going to simplify, no, this one, so this is just equal now to the integral of this quantity, no, this is x squared plus 2y, we distribute the negative sign here, so minus x squared minus 2c3, and this is dy, okay, okay, so proceeding here, so we have this following calculation, no? Okay, so this is also equal now to the integral of this quantity, so this one x squared minus x squared, no, so this will be cancelled out, so this is 2y minus 2c3, okay, and this is dy, okay, so distributing the integral, so this is integral of 2y, and this is dy minus integral of 2c3, and this is dy, okay, and this is just equal to, so we have here, no, we extract the 2, so integral of y dy minus, we extract no the constant no 2c3 integral of your dy, okay, and this is just equal now to 2 times this, okay, so u to the n plus 1 over n plus 1 plus constant, so we let u here no, we let u equal now to y, and your du is equal now to dy. Again, you use this integral no of your u to the n du is equal now to u to the n plus 1 over n plus 1 plus c, okay, so we will use again it here, so this is y squared no, and then this is 2 plus our constant here will be, since we have c1, c2, c3, and we already have c4, so we will assign here as c5, okay, c5, okay, and then this is minus 2c3 times the integral of your dy, which is just equal now to your y no, integral of dy is just equal to y plus your constant we use here c6 no, okay, and this is just equal now, so cancelled out, so this is y squared plus 2c5, and then minus, we distribute no to each term, so this is minus 2c3 times y, and then minus 2c3, and this is c6, okay, so we have now this equivalent no for this integral of this quantity n minus partial derivative with respect to y of your integral of mdx dy. So therefore we can say that our integral no, our integral of your mdx plus no, plus we have here this integral of this one, we have mdx plus the integral of this quantity n minus partial derivative no with respect to y of your integral of mdx, okay, and this is dy is equal now to c, will just simply equal now to, we substitute no the value of our integral of mdx no, which is equal to this x squared, which is just equal now to this x squared y, so we already calculate this one no, plus 2 c1 y, okay, then this is minus x cubed, okay, and this is minus 3c2, okay, so this we calculate this one no, in our previous slides, and this is plus no, plus of this one here, okay, which is the equivalent of this integral no here, so plus this quantity y squared plus your 2c5 minus 2c3 y, then minus this 2c3 and c6, and this is just equal now to, so we have quantity here, and this is just equal now to c, okay, so after this one we will separate no, we will separate those constants and those variables, okay, so we will proceed here, okay, so from this we have now this values here, so which is equal now to, okay, so this is plus, no? So again we will rewrite this one here. So this is x squared y, okay, plus 2c1, and this is y, minus this is x cubed, no, minus 3c2, and then plus, we distribute this one every term, no, so this is y squared plus y squared, okay, and then we have plus 2c5 plus 2, this is c5, minus 2c3 minus 2c3 times y, and then we have here minus 2c3, and we have here c6 is equal now to c, okay, and this would be then equal also to separating all constants and variables. So we have here x squared y, so we're done with this, and then we have now this, we have here x cubed, no, so minus x cubed, okay, and then after that we have here plus y squared, no, plus y squared, okay, and then we have here this another y plus 2c1 plus 2c1, then this is y, okay, and then we have this constants, no, so minus 3c2, and then we have here plus 2c5, so we are done with this, minus 2, okay, so we have, excuse me, no, 2c3y, okay, we have 2c3, then we have y, then minus we have here 2c3, and we have here c6 is equal now to constant, okay, so afterwards we will simplify it more, no, so we have x squared y minus x cubed plus we have here y cubed, y squared rather, plus we have here 2c1y, no, and we have another 2c3y here, so we have here minus 2c3y, no, and then afterwards all are then constants, no, so minus 3c2 plus 2c5 minus 2c3 c6 is equal now to c, okay, and we will assign, no, let, we are going to assign let c is equal now to, so we will assign our last constant is 6, so let us assign let c7 is equal now to this minus 3c2 plus 2c5 minus 2c3, and we have now this c6, no, so minus 3c2 plus 2c5 minus this one, so therefore we can say that our equation will then be equal to x squared y minus x to the cube plus we have y squared, and take note, no, this one plus 2c1y minus 2c3y, okay, and we have here c7, no, we will assign a constant, so this is plus c7, okay, is equal now to our constant capital C, okay. Okay, so proceeding, no, with our calculation. So as you can see it here, we have the presence of 2c1 and this minus, no? So we have here, take note, we have here 2c1 of your y, and then we have here minus 2c3 of your y, no? So if you can still remember, no, that for the first integral, no, in our direct solution, we have here the integral of mdx, no, and we are going to have the second term, no. If you can still remember this one, we have here the value of your n, no, we have n minus the partial derivative of with respect to y, no, of this integral mdx, okay, and then this is dy is equal to c, okay. Upon solving our integral, no, integral of mdx, our constant involved here is our c1 and our c2, okay. And upon integrating, no, and solving this integral of mdx, our constant involved there is our c3 and your c4, okay. So still we have the same integral of mdx, no, but we will just assign c1 and c2 here since this is the first integration. And during our second integration here in this term, we assign c3 and c4. So we can say that your c1 is just equal now to your c3, and your c2 is just equal now to your c4 here, no, since we are integrating at the same m, no, with respect to x, okay. So because of this one, 2c1y minus 2c3, which is here, no, 2c1y minus 2c3, since our c1 is equal to c3, so we can say that this will be cancelled out, no, this will be equal to 0, okay. And our equation will then be equal to x squared y minus x cubed plus your y squared plus c7 is equal now to c, okay. And this will then be equal to x squared y minus x cubed plus y squared equal now to c minus c7, okay. And a constant minus a certain constant is just equal to a constant, so we will assign this c minus c7 equal now to our final c, okay. So we can say that this will then be equal to x squared y minus x cubed plus y squared is equal now to a constant c, okay. And this would probably be our answer, no, for this given differential equation, which is equal now to x squared y minus x cubed plus y squared is equal to c, okay. So we are done solving, no, this given differential equation using the exact, no, differential equation or method. Okay, so I hope you have learned something, no, today regarding our topic exact differential equation, and I would like to cite my references, no, of Nagli and also of Proven de la Fuente et al. I use their books, no, as my reference for this topic today, the exact differential equations. And before we end, I would like to thank you everyone, no, for having time, no, on listening and watching my lecture video. And our next topic, no, for the next video will be the non-exact differential equations. Again, thank you very much, and God bless and keep safe everyone.